So what else do we know in this problem at the moment? We know we're supposed to find dz dt, but what about dx dt or dy dt? We actually have both of them already, right? 16 miles per hour is dx dt. It's the way that the horizontal distance for u is changing with time. So we need to find this, but we know, knowing that dx dt is always a constant 16, dy dt is always a constant 12. Right? So if I now attempt to differentiate this with respect to time, so I'll certainly get the dz dt derivative coming out of here, which is what I want. We also kind of anticipate that the dx dt and dy dt derivatives will pop out of the left-hand side, but when they do, that's fine. It's information I already know. I'm going to replace them with 16 and 12 when I get the chance. So let's go ahead and differentiate both sides with respect to time, and then see what that new equation looks like. Again, we've related the distance between you and friend to your distance and friend's distance, right? So once we take the derivative, we'll have some sort of, again, related rates. We'll have a relationship between rates, between the change of the distance between you and the change of the two distances themselves, right? The horizontal and vertical distance. So taking the derivative of both sides is looking like implicit differentiation here. So I'll take d dt on both sides. Again, where I'm viewing every single variable as dependent upon time. So therefore, x is a function of time, which makes sense, right? You're moving rightwards, right? So as time progresses, x changes, right? And friend is moving northwards, so therefore, as time changes, the y value changes. So it makes sense that x and y are dependent upon time. These derivatives are not trivial. So to this distance, right, certainly if x is increasing and y is increasing, this hypotenuse is just getting larger as time proceeds. And therefore, z is also dependent upon time. So therefore, they are functions of time and need to be treated as such. And so therefore, the chain rule will affect them all. So this should be 2x dx dt plus 2y dy dt equals 2z dz dt. Again, for each and every one of these, because for all three of them, x, y, and z are all dependent upon time, the derivative of what I'm considering an inner function, right? X is inside the squaring function, y is inside the squaring function, z is inside the squaring function. All of the derivatives must emerge through the use of chain rule. Okay. Now we just solve for the one we want. We're going to isolate the dz dt derivative. Okay, so it looks pretty straightforward. I'll just divide both sides by 2z. All right, so I'm going to divide by 2z, but I'm going to put dz dt on the left just to make it look a little bit nicer here. Okay. I like to have the thing I'm solving for on the left. That's just a personal preference. So dz dt should equal 2x x derivative plus 2y y derivative over 2z. Every term has a 2. Let's just get rid of that. So now we have x dy dt, sorry, x dx dt plus y dy dt over z. Okay, so this is what we're looking for. Again, one derivative expressed in terms of another. In this case, it's two others, but it's still related rates. This rate here is related to these two. Okay, so now to finish it off with dz dt evaluated at x equals 4. So dz dt at x equals 4. That was the most explicit value we knew. We said it also corresponds to t being a quarter of an hour. But I'm just going to write as x equals 4 here for a moment. And over here, that means I get to fill in x with 4. That's useful. dx dt we said is always 16. Do that from the beginning. Y we do not have at the moment. but dy dt is 12. Okay, so I fill in 12 there. That was always known from the beginning. You just got to realize that you know it in a sense. You got to realize that 12 is really the derivative of y. It's important to realize that in terms of this notation, so you'll know how to fill things in when you get to the end. So we just need y and z. Okay, so if x was 4, we said you've traveled for a quarter of an hour. If you travel for a quarter of an hour, then friend has traveled for a quarter of an hour. If friend travels for a quarter of an hour, how many miles has he gone? It looks like 3. Okay, he only went 3 miles. So we should have a 3 here for y. Okay. 12 miles per hour. For 1/4 of an hour, you should have moved 3 miles. Now z, we don't have. We need to get z. But we know that z squared is equal to x squared plus y squared. So now we can fill those in and use the original equation that we got the derivatives from. So x squared was 4 squared at this moment, right? Right when x is 4, right when x is 4, we just said that y is going to be 3. Right? So that will totally determine now what the hypotenuse squared is. So 5, right? 16 plus 9 is 25, and the square root of 25 is 5. So 25 is z squared. It's a 3, 4, 5 Pythagorean triple. 5 equals z. Now truly, z could have been plus or minus 5, but because of the context, we know that z is a positive 5. It's the distance between you and friend at that moment. So therefore, this has to be a regular 5, not a negative 5, even though theoretically it's possible from the equation. So now we have everything filled in. We just need to compute the value. So let's see what we have here. 16 times 4 is what? 64. 64 plus 36 is 100, it sounds like. Sounds reasonable. 105 is 20. So we have 20. Now what units will it be? Again, without going back through and writing all the units for here, x, y, and z, all the units, right? Miles per hour, miles, miles, and then trying to compute out what that is, look back what you have here, dz dt, dz, z, since the distance between you and friend should be miles, and time has been measured in hours for the whole problem, this is also miles per hour. Okay? Without having to resort to calculating the new units from all the old ones. So there is our answer for that one.